And we're getting there through all of these different reactions. How about a reaction with an amine? See, I'll leave that there in case we need to still have that. Let's take an ester and react this with a primary amine. So NH2 connected to some R prime group. And here it looks like we're actually generating an amide. So here we have an ester forming an amide. And I'm assuming this is probably going to follow a similar reaction mechanism to those that we've already seen. Let's use something, we'll just stick with methyl groups because they don't take up much space here. And how about we react this with, so let's use an ethyl group just to make it a little bit different here. So this ethylamine. Now we saw before that these amines, they're more nucleophilic than some of the alcohol-containing compounds like the alcohol or water. So they actually oftentimes will react without the presence of added acid. So let's just have this act as a nucleophile, attack. We have our tetrahedral intermediate. And we drew an oxygen. So I might have something now that looks like this. And now what we need to do is to kick out our leaving group, and we'll have to take care of a proton transfer in the end to end up with our amide. So let's just kick out our leaving group, reforming the carbonyl group. Let's move this around here. And then an acid-base reaction is at some point this will quickly grab one of these protons. So now we formed our amide in this case. And we could have a lot of variations with this depending on what sorts of alkyl groups that we have here. Just happen to use ethyl in this particular case. You could have much more sophisticated R groups here. You could have two R groups, and so you'd have another R group at this position. And this is the last, leave that up there. One more. And how about this idea of transesterification? So let's take this ester, this kind of boring ester that we've been using all along, and if we were to react this with an alcohol in the presence of an acid, we actually formed a different ester. So it looks like this alcohol here is now this part of the ester. It's supposed to be a six-membered ring. So this is known as transesterification. We we'll convert the ester from one ester to another ester. So I'll be quiet for a minute here. I'll give you a chance, if you would please think about the mechanism for this reaction. It follows exactly what we've seen before. Notice we have just a little bit of acid and an alcohol. So I'll give you a head start if you would please think about what the mechanism will be for this transesterification, and I'll start writing it out here in a minute. So hopefully everyone is coming up with a similar mechanism. So really nothing new, just like what we saw before. This time we happen to have HCl, hydrochloric acid, rather than our generic hydronium ion, but we're going to use this to protonate the carbonyl group, make this carbon much more electrophilic. So our weak nucleophile, this cyclohexanol, can then act as a nucleophile and attack. Now a series of proton transfers take a proton off, put a proton on this group over here to make this a good leaving group, so that we can then kick it out and then deprotonate our protonated carbonyl group in the end to form the transesterified product. And one of the more details but important features of these reaction mechanisms, as I mentioned, here we are using HCl as opposed to just H3O+, which oftentimes is generated by using water with a bit of sulfuric acid in it. And that one's oftentimes used because the chloride could do other things in a reaction that you don't want, where as the conjugate base of sulfuric acid, the sulfate ion is much less likely to do that, much less reactive. And then notice how water seems to sneak in here as well. And you'll see this in a lot of these reactions because hydrochloric acid, when you have the bottles that you've used in the either organic or gen chem labs, that's actually HCl in water. HCl itself is a gas, and so it's an aqueous solution. So in the lab, if you were to add a couple of drops of HCl, say, to this reaction, you have this in a flask and this alcohol in a flask, mixing them together, and then you add a little bit of HCl, you might have some other solvent in there, that you're adding water. So I know sometimes in our organic mechanisms, it seems like things kind of appear out of nowhere, but there's a reason for that. Good question, Sage. So why doesn't this group just leave as it is? So it's an excellent point. We can use this to summarize a couple of things here. Is notice this reaction is done under acidic conditions. The main the difference is acidic versus basic conditions. So under these acidic conditions, we have positive formal charges throughout the mechanism here, and our intermediate here on the upper right, notice, is a species that doesn't have any formal charge on it. So we don't really have a good driving force to kick out this leaving group as methoxide under these acidic conditions. So instead, it's going to be more energetically favorable in the presence of acid to protonate first, make this a good leaving group, so that now our neutral oxygen with these lone pair of electrons on it can then kick out the methoxide. So this is a much less reactive species as it is to start with. But for those who, I won't draw the whole energy profile, but if you're looking at delta G as a function of some reaction coordinate, you'd have the neutral species, let's just say, existing, in some well here. This would be the neutral species. But what we're going to see is that the negatively charged species is going to be much higher in energy. So when we have a negative charge on it. And so if I scroll back up a little bit here, where was it? How about this case, the saponification reaction? Here now I have this negatively charged species. So that's going to be higher in energy, so I can then energetically have it be more favorable for it to kick out the methoxide. All right, excellent. So it's the difference of basic and acidic conditions. So great point. Okay, and then building on that, so those are the reactions of the esters that we're going to consider. So these are very important functional groups. There's a lot of rich chemistry that goes on with esters. They're very useful synthetically. You can make them a number of ways. The Fischer esterification is a very important reaction. And then you see these variations on it where we can convert the ester back into the carboxylic acid, or here we can convert the ester into another ester, and so on.